morning. I want to start this last presentation just to finish the cycle of 4 lectures regarding powder metallurgy for beginners, trying to explain that with this we try to complete 4 short lessons for people who want to approach to this fantastic technology. So today I'm going to talk about the properties and how to improve the properties, because usually people think in powder metallurgy like a technology that can produce cheap parts, long series parts, but not with high performance properties. So first, I wish to talk about how we can be the final properties that we can expect from a PM part. At the end, this depends on the right decision on the 3 main steps of the process: powder selection, pressing, and sintering. And in some cases, pressing and sintering will happen at the same time. So in that case, we will fall in the typical tetrahedron of the material science and engineering, in which we have to relate the properties, the composition, the process, and the powders that we are using. So in this transparency, I want to compare what we can expect from the conventional forged materials and the conventional PM materials. In conventional forged materials, usually we have a microstructure with a fully orientated microstructure with a texture in one direction, which is perpendicular to the forging direction. And on the other side, in powder metallurgy, we see a porous material, because usually we have used a press and sintering process in which we can reach the full density. So we have a microstructure which is with an isotropy. We don't have a special texture like in forged materials, but we have these black points that try to represent here the porosity. So this is the starting situation from the worst possible materials obtained by powder metallurgy, but we can improve the performance trying to reduce the porosity. That is possible with some technologies, and even trying to reduce much the grain size. Of course, as soon as we approach from left to the right, we increase the performance, because we are eliminating the porosity and even reducing the grain size, but usually we also increase the cost. We are moving from the topic of the field of application of powder metallurgy regarding to the inexpensive material with low cost, high precision, and high productivity, to the materials which are the better possible material for one specific application. So another way is just to try to move in this graph, in which we can plot here the strength against the dimensional tolerances. The conventional powder metallurgy could be found in this part of the figure, in which we have from medium to very good dimensional tolerances, and from low and very high strength. But of course, in this part of the graph, we could find the materials with low porosity and fine grain size. And here maybe we have the materials, here we have the materials with low porosity and low grain size. In this case, we have medium or poor dimensional tolerances and high strength. And here we could have the conventional PM materials with very good dimensional tolerances and low strength. So let's go to compare PM against an alternative process. And we like to use this graph, in which we can compare the raw material utilization and the energy requirements per kilo of finished part, comparing different processing methods like casting, powder metallurgy, extrusion, forging, or machining. As you can see here, the raw material utilization of powder metallurgy is much higher than any other competitive technology. And also, the energy requirements for kilo is much lower than most of the alternatives that we can use to get the final part. The worst situation in that case is for machining, in which we have in the order of 40–50% of percentage of raw material utilization, and the energy requirements are much higher than in the other methods. Here we have one example. We mentioned in the previous lecture the year for the oil pump. This was the first press produced by Powder Metallurgy, and in this case, the cost advantage over machining is in the order of 70%, because here we don't lose any raw material, because the final part is the sinter one. We don't need sometimes, most of the times, heat treatments or any further operation after sintering, and the energy consumption is much lower than in machining. This is another interesting part, which is the synchronization hub in the manual transmissions of passenger cars, in which here, depending on the process that usually in Europe is a little bit different than the United States, but the advantages in terms of saving is in the order of 57 in USA or in the order of 40 in Europe over machining. Here we have again the previous one, in which we see here how we can move from conventional powder metallurgy to the advanced powder metallurgy. Let's go to this route. Well, how we can improve these properties in PM materials? We can improve the properties in different ways. Here we can talk about 6 possible different ways. One, we can improve the properties without increasing the density level. We can improve the properties increasing the density, but from high green density levels. What we do is to use the pressing step to improve the properties more than the sintering step. We can, of course, improve the properties in the sintering step by sintering activation. Another way is one specific way to activate the sintering, which is using pressure and temperature simultaneously. And we can inhibit the grain growth during sintering. This is another way to improve the properties. And at the end, we will talk a little bit about the additive technologies. So let's go to the first thing, how we can increase the density level and improve the properties. We can act over the alloying system, we can act over the microstructural system, and we can act over the grain size. Here we have one example of the way in which we can improve the properties without increasing the density level. Yes, it's just acting on the alloying system. I mentioned in one of the previous lectures that we can fit the process with different kind of treatment of the powders. We can use mixed powders, diffusion bonded plus pre-alloying powders, diffusion bonded powders, or even fully pre-alloyed powders. Here we have the tensile strength against the alloying elements, the percentage of alloying elements in 1 PM steel. And you can see here that depending on the method in which we fit the powders in the process, we can have much higher tensile strength for the same amount of alloying elements. This is one way in which we can improve the properties without increasing the density. For the same density level, we can have, for the same level of alloying elements, much higher tensile strength in some cases than others, just taking into account the way in which we put in the system the powders. Of course, we can improve properties without increasing the density level through heat treatments. Here we have one example in which we have the same material in 4 different conditions, and we have here the UTS and the GLC strength and the strain. This is the strain, and here we can see how in some conditions, heat treatment conditions, we have much higher properties. This is quite well known for all metallic materials. We can act over the microstructural system. How we are mentioning about that? We can modify the microstructure not only through the heat treatments. Heat treatments can modify the microstructure, but microstructure in PM materials are composed by 2 different families of things. One is the microstructure itself. The conventional heat treatments act on the microstructure itself, but in PM materials, we also have porosity. And through the heat treatment, we can modify the roughness, for instance, of the porosity. And modifying the roughness of the porosity, we will improve also the properties without moving in some way the density level. Another way is we can increase the properties without increasing the density level, acting over the grain size. Here we have, for instance, one example of what I want to try to explain. If we use, for instance, mechanical alloying, we obtain grains, particles, powders with a very fine side of the grains. So that means that after sintering, if we start from side grain of grain size in the order of nanometers, of course, during sintering, we will increase this grain size, but much lower than in any other alternative. Other ways to reduce the grain size is using rapid solidification. This is some methods to produce rapidly solidified particles, or in this case, small fibers that later can be grinded to obtain powders. But in these ways, we can get a really, really fine grain after the process. We can improve properties, increasing density, but from the pressing step in green level. So here we have some examples. One example is the warm compaction process. Here, what we do is to heat up the pressing tools and even the powder. We can heat the powder and the pressing tools. Heating in that way, just increasing the heat, increasing the temperature of the powder, or just a little bit from room temperature to 100, 110 degrees in the case of iron, we will improve a lot the density after the pressing, because we reduce strongly the yield strength of the powder, and in that way, applying the same pressure, we can reach much higher density. For instance, in conventional powder metallurgy, after pressing, we used to have no more than 701 grams per cubic centimeter. And using warm compaction, after the pressing, we can have here in the order of 7.4 or even 7.3, 7.4 grams per cubic centimeter. And even these green parts can be green machining. That is impossible to do with conventional pressing methods. Here we have some results of what we are talking, just using warm compaction, just from green density, increasing the green density, we can improve the strength in a big amount of units. Another way to improve the green density is the so-called high velocity compaction system. What we do here is a real cold forging process. What we have a hammer, we put this hammer in some specific distance from the die. We leave we bust the hammer into the die, and we produce a shock into the powder, and we increase a lot the green density. In this case, as I mentioned before, with one compaction, we can go from a green density of 6.6, 6.8 in a conventional material, and we reach after the green state, after the one compaction, after the high velocity compaction, densities of 7.5, 7.6, much higher than the conventional that we can reach using cold compaction, conventional cold compaction. Of course, we can improve properties activating the sinter process. We can do it in different ways. One way, of course, is reducing the particle size. If we reduce the particle size for the same temperature, we can reach much higher density as much as we decrease the particle size. With low particles, for instance, 5 microns, 10 microns, against 20, 30, 40, 50 microns, we can reach full density, maybe with 100, 200 degrees lower sintering temperature. So this is a real advantage to use fine particle size. This happens usually in metal injection molding. In metal injection molding, we have a process that after the debinding, we have maybe 40, 45% of porosity. So that means that we have a lot of surface in the brown part. This surface promotes a very activated sintering process. But we have a second way to activate the sintering process, because the powder that we use conventionally in metal injection molding is much finer than the conventional press and sinter powder. We are talking that in conventional press and sintering process, we used to have powders with an average size of 80 microns. And here in metal injection molding, we use an average size of in the order of 15, 20 microns. So at the end, in a conventional press and sintering, we have more or less 10% of porosity, and in metal injection molding, we can have here less than 3, 4, 5% of porosity. Of course, we can improve the sintering method, or we can activate the sintering process by liquid phase sintering. In liquid state, the diffusion takes place much better than in solid state, and using liquid phase sintering, transient or permanent, we will activate a lot the sintering. Here we have some examples of conventional materials in which we used to employ liquid phase sintering in the process. This is a tool steel. This here we have a cemented carbide, which is a typical cemented carbide. And here we have composites, which is made of copper matrix and molybdenum disilicized as reinforcement. We can apply pressure and temperature simultaneously. The other day, just in the previous lecture, we mentioned 2 ways in which we can apply pressure and sinter and temperature at the same time, and we can reach at the end fully dense material. One is hot pressing, other one is hot isostatic pressing, or spark plasma sintering we mentioned in the previous lecture also. We can also inhibit the grain growth during sintering. And I mentioned before a couple of ways, but this is during sintering. Before we were talking about the powder development. In powder development, we can reduce the grain size through mechanical alloying or rapid solidification, but even sintering can be made in a way in which we don't allow to the material to grow the grain, because we perform the sintering process in a highly, let's say, activating method way and in a very short time. One possibility is the so-called microwave sintering. Microwave sintering was developed many years ago for ceramics, but in the latest, in 1999, in the latest 20th century, it was developed also for metals. Using these susceptor materials in a ceramic tube, you can sinter under microwaves heating system, even metals. In this way, you heat up and cool down in a very fast way, and you don't allow to the material to have time to grain growth. So that means at the end of the process, you have a really very refined grains. So that means much better mechanical properties. Of course, I mentioned the day before also spark plasma sintering. Here we activate the sintering for different reasons. We are applying pressure and temperature simultaneously, but we inhibit the grain growth because spark plasma sintering heat up also in a very fast way, and the dwell time that we maintain the sample at high temperature is very short. Just for comparison, we can say that hot isostatic pressing to reach the same level of density and the same level of microstructure, the same kind of microstructure, need in the order of 2, 3, 4 hours to reach this full density. In a spark plasma sintering, we can reach the same, absolutely the same level of densification, just with a few minutes of dwell time. Sometimes 10 minutes, 15 minutes in comparison with the 3, 4 hours that we need in hot isostatic pressing. So that means spark plasma sintering can produce full dense materials, but also with very fine microstructure without any grain growth. Just for finishing, just to tell that powder metallurgy is a technology really flexible. We can use for the same material many different PM technologies. Here is one example in which we have a gamma aluminum titanium aluminide processed by hot isostatic pressing on the left and spark plasma sintering on the right. See that the microstructure here shows some grain growth of some of the phases, and here we have a more conventional basket microstructure for this kind of materials. Here we have the same more or less the same microstructure with the same material, which is iron-based reinforcement with carbides or carbon nitrides in this case. On the left, we have reached the microstructure of this composite, pressing at 700 megapascal and sintering in vacuum 400 degrees during 60 minutes. And on the right, we can reach the same material but sintering in a spark plasma sintering equipment, 1100 degrees, 60 megapascals, and just 10 minutes under vacuum. So you can compare here the flexibility of powder metallurgy as technology that can provide many different possibilities for the same material. This is one typical example also. This is high-speed steel. On the left, manufactured by horizontal pressing. On the right, metal injection molding. You see, microstructure is quite similar. Maybe in this case, even metal injection molding has a lower grain size in the carbides than in the horizontal pressing. And just let's go to the most recent kind of technologies just to develop advanced materials from powders, which are the additive technologies. As I mentioned in the previous lecture, we have different ways to use the additive manufacturing process. We can have beams of high energy, like laser or electron ion beams, in which we have the so-called powder bed systems. The other day we mentioned also the other methods like powder feed or even the binderless methods. So if we go just as a summary, we can say that powder metallurgy can produce porous material, as you can see here. This porous material used to have much better productivity than in other kind of materials, but lower properties. But from those porous materials acting on different things, like the alloying system, like through the heat treatments in the microstructure, or even to the grain side, we can improve the properties and we can change the microstructure, improving the properties. Also, we can reduce the grain size and reduce the level of porosity, starting from high grain density materials or activating the sintering process. We can also reduce the porosity even more, applying simultaneously pressure and temperature. And we can go to systems like in spark plasma sintering, in which we can inhibit the grain growth. And finally, we can obtain full dense materials using additive manufacturing. Maybe we can develop some defects, but this defect even can be eliminated by for instance, by hot isostatic pressing. So at the end, you see, we have, with the same material, we can develop different kind of microstructure with different levels of porosity that allows different levels of theoretical density to materials with density more near to the theoretical one. And we can get really advanced materials using powder metallurgy. So we have a flexible process with a wide range of materials, with a wide range of properties, microstructures. So that means a lot of field of applications. As you can see here, structural parts, biomaterials, cutting, brushings, etc. So thank you for your attention. This is the last lecture for this short course for PM for beginners. And if you have any questions, you can mail me or you can use the platform of YouTube just to allow to give me your message and your questions. Thank you very much. And I hope that you will find this technology, a nice technology to be part of this world of powder metallurgy world. Thank you very much.